So window, all right. So here's what we're going to be focusing on today. I'm going to open up an example sketch because we're going to start learning how to do a little bit more with some of the serial commands. We're going to be using serial begin again today. But one of the things we're going to do is we're going to do an analog input as a starting point. So we're going to do censored reading. They aren't going to have a good example for us to start from. So we're going to have to go through a couple steps. Yeah, we're going to have to pull some of these commands because it'll be a little bit easier. So we're going to start with an analog input. So you're going to go to examples number 3. So under file examples number 3, we're going to start with analog input to give us an idea of how to begin. There are a couple things. In this case, it's looking for a potentiometer. So there's a circuit that needs to be connected to this. We've already got some onboard sensors, so we're going to do things a little bit differently here. One of those is going to be, and I'll switch to this. So we've still got a few jumping in. I'm going to switch to this window. There we go. So we're starting from file examples analog input from number 3 from the analog set of examples. Most of the things that you guys are going to encounter are going to be analog by nature. So digital signal is a little different from analog in that it's on, off, 1, 0. Analog is variable, much more so than, so think like a volume knob, for instance. A volume knob is a variable, what's called a variable input. So there's a couple things that I think will help to clarify some of what we're looking at. So there's a couple things that are noted here. So we're starting with analog input from file examples number 3, analog input. What this does is gives us a starting point to see what an algorithm looks like. So rather than spending a lot of time thinking about what should an algorithm be, the pseudocode for this would look something like read the input, display it to the user. Great. How do you actually put that into real code? And that's what we're going to focus on today, is how to actually do sensor input. So we want to have an analog input by reading some kind of analog sensor. In this case, he's using pin 0. So we're going to look back at the examples on the board here. We can use any of the different pins. All of the values that have an A next to them are analog inputs. So we're going to be doing some analog input, and one of the easiest ones to use for today, let's see, might actually be analog input 9. because we can start looking at how do we look at the temperature in the room where you are? How do we do some conversion for that? But first step in that process to build a sensor, and especially to do some calibration and things of that nature, we have to have an idea where these are at. So where the input parameters are at. So the way that he's got this set up is a potentiometer. So let's go back real quick to what he's doing here. So he's looking at analog pin 0 and turning on and off the LED on pin 13. So the red LED on pin 13, we still have the red LED on pin 13, so we can reuse that part of the code just for the sake of simplicity today. But we can also start learning how to use the neopixels and colors for the neopixels and stuff as we understand sensors this week, and how to monitor what that output looks like. So the potentiometer is something we're not going to bother with right at the moment. It's the same thing that you guys would recognize as a volume knob. So it's a knob that you turn. It varies the voltage on one of those pins from 0 to 5 volts and back and forth. And he has the LED on pin 13. So this part of it we actually don't need. So I'm going to cut out this part of the comments. And in this case, I'm going to replace this with Circuit Playground Express is actually our circuit, because we do have a circuit that's involved. You do have to have some kind of a circuit for there to be a sensor and all of those sorts of things. So there's in this case, he recommends an external LED with a 220 ohm resistor attached to the ground. We are using the onboard pin 13 LED, and the LED is optional, so we know that that's not particularly helpful. Okay, so this is if you're shamelessly stealing from somebody else's code, you should probably give acknowledgments. That's a thing. You guys are probably surprised to learn that people were coding all the way back in the ancient of times, back in 2011. I think some of you might have been born that year. So this is the start of what we're going to be working on. One of the things that we need is we are going to need a sensor pin. And in our case, because we're using the Circuit Playground Express, I'm going to have you guys use analog 9. So analog 9, select the input pin for, in our case, this is an onboard thermistor. So it's a thermal resistor, hence the term thermistor. It has a calibration for values that we're using currently. We're using LED pin as 13. It doesn't matter whether these are capitalized or uncapitalized, so long as it's the same for a variable name. Then we're introducing something new called a variable for sensor value. And this is where we're going to store the sensor data, right? Because think about the incoming data as something like a stream of water. as soon as you turn on the oh, that's interesting. He is not using, yeah, because he's looking for output. He's not using the serial monitor. So we're going to add in the serial monitor. Coding is not a good thing for somebody that has ADHD-like tendencies. They will never get to program completion and execution. So that's going to be hard for some of you, I imagine. The sensor values, the reason we need a variable there is as soon as we turn on that serial monitor, it is like a faucet has been turned on, and we have to do something with the incoming data. So you need some kind of container to contain the water that's coming back through the serial port. You have to be able to catch it and do something with it. So you need a couple pieces in order for all of this mess to work, because there's a lot going on. So sensor value is important. We are going to be using this, and we've got quite a few examples of how that's being used. We've got quite a few examples of how that's being used. So there's a couple things that are happening here. One is we are looking we're looking to store information to this sensor value. Another is in our setup, we are going to use LED pin as output. But we also need to be complete and rigorous here. We really need to do a couple of things, one of which is going to be we need to start we need to open the serial port. So serial dot begin, default of 9600, close that line. We need to comment so that we know why we're doing this. Which is kind of like turn on the faucet. Can't do anything with water until you turn on the faucet. So you have to open the serial port. So we're going to be doing something different than what this code was intended. This is why we're going to cut this portion of the code, because by the time we're done, almost none of this is going to resemble the original code. So we've got our LED pin set to output. We've got serial.begin so that we open the serial port. The other thing that we have to do in our code that runs once is we need to set our pin to input for A9, and this is going to help. This is sensor pin input. So we want to define this as input in order for us to have code that's going to be at least in part complete. Will the code run without this line? Yes, most of the time it should run correctly without this line. Okay. Will that be, will that be 100% of the time? Perhaps, perhaps not. If the board is reset and the sensor pin isn't set to input, many of the analog pins can be either input or output. So we want to make sure that we've got the correct declarations originally. So setting the pin to input establishes, hey, this is what we're going to be using it for. It should be on the Circuit Playground Express input by default. It really can't output there very well because there's nowhere for it to output to. So you could make an argument that this is redundant, but I'm trying to teach you guys good habits. So we want to make sure that that's defined as a known input pin. And it is a 9, no longer a 0. The sensor value, we start at 0 so that we don't start with some gibberish in the memory to create issues, sort of like what we were seeing last week with some of those output values. In the loop, we're going to read the value from the sensor. Sensor value is, instead of digital read, we're going to do an analog read, or instead of serial read. This is where we're going to be using for this. I think we can use an analog read on this, and instead of serial read. So serial read reads what's coming back from the serial port. The data, because we're doing input on this sensor pin, we need to be reading that sensor pin using an analog read. So this is a function that's happening on the board. This is not happening on the serial monitor. But then we are going to have to do a digital write to the LED pin to turn it on, to say, hey, we have a reading. Then delay the program for X number of milliseconds. So you can pass not a number, but a variable into the delay function. So long as it's an integer, whatever value you pass is fine. If you were to change this to a string or some other thing, data type mismatch, you'd have all sorts of errors. But as long as it's an integer, the reason we will mostly deal with integers is because for many simple applications, they are the most useful, especially for getting the concepts. Later on, you can do fancy crap. Right now, you need to focus on how do you do the simple stuff well and understand what's going on. So delay by sensor value based on what this reads. You can set this as a fixed delay so that you have some control over what's going on. The digital write then will be a little bit, we'll set the LED pin to off. Then you have another delay. There's one more step that we need to do here in order for this to be useful for our purposes. Does anybody know what that is? Can anybody spot what's missing for us to be able to see what the actual sensor is reading?
Are we missing a print line?
Yep,
or
exactly.
Print statement?
So we can allow it to do the delay, but before the delay, we want to, so right up here after it turns the pin on, we want to go ahead and write the sensor value. And there's a couple reasons why we want to do this. There's a couple ways that we can also, there's There's a couple things that we can also print. So we'll start here, serial dot, and then you'll have all of these suggestions to pick from. Again, the fact that you guys have all of these suggestions is utterly silly, but they've made this so much easier on you. The days of having to manually type things are almost as far gone as the days of having to do programming on punch cards in sequences. Crazy talk. So serial print line, we want to print the sensor value. So we want to print sensor value. So sensor value, we want to print, and then for this, I'm going to leave it at the default because it's going to default to the decimal form. So that's okay with me. And we want to make sure to close that line with our semicolon there. So serial print line sensor value. That will give us an idea. You can also say for the context, we're going to do another serial print line, and we're going to say we're going to encase a string in quotes. So something simple like sensor value is I don't want you to think of this as a live data stream, so I'm going to make a couple more changes to the code here. So I'm going to say is currently, and then I'm going to change the code I'm going to change this to have a space. I'm going to change this to a serial.print and then a serial.print line. Just because of how I want it to display. I want it to display this string first, then the value, and then go to the next line, or do a carriage return is what that's called. So serial print line sensor value. Then I'm going to set the delay to be, this is cute for the circuit that he was working with a potentiometer where you change the quote unquote volume knob, and it adds or decreases the amount of time that you wait for the sensor to turn on and off. So sensor value is useful in that context. We're using it as a storage system. So I'm going to change this to be, instead of storing a value for a longer period of time, I'm going to shorten it by saying we're going to do 350 milliseconds, then set this pin to low, 350 milliseconds, so that the LED is off. We have a little bit of delay in our data stream so that we can watch what the sensor value is currently. And we're going to be able to see what's happening with the value as we like blow on the pin, or hold it in front of our laptop fan or something like that. Question?
Yeah, so beforehand when we had the sensor value as the delay, it would just be no delay because the sensor value equaled 0.
So it would be 0, but so it was started at 0. That's called initializing the variable to give it a baseline value at the beginning of the program. So in the setup, we don't touch the sensor value, right? In the loop, the first thing that we do is reassign the sensor value to whatever that sensor pin reads. So if the potentiometer was set to 4,000 millivolts, right? 4 volts, it would put in a delay of, I believe it would put in a delay of 4,000 milliseconds. I think is how that one was going to work. So what that would do is that sensor value would read every time it goes through the loop what position the potentiometer was in, meaning anywhere from 0 to 5 volts, so 0 to 100%. And based on the percentage of how far that potentiometer was turned, right, just like a volume knob, it would delay by that many milliseconds, basically. So the higher the value, the higher you turned it, the slower it would go. The lower value, the lower you turned it, the faster it would go. That's how that code was originally set up. So in our case, we're looking for data from a temperature sensor, which is going to be scaled differently. And what's going to be interesting to you guys is what we read back on the serial monitor from this example. And then when we stick it in the stream of an air conditioner, or when we stick it right next to the outlet for our computer fan or something, right, we're going to see a change in what the sensor value is. When we blow on it, we're going to see a change. If we put our thumb over it, we're going to see a change in the value, right? Because most of those rooms there in Phoenix are going to be, 135 degrees Fahrenheit, right? So not really, but seems like it some days. You are probably actually in a room that is in the ballpark of 74-ish degrees Fahrenheit, give or take a couple, for the most part. So the value that we're going to get back, though, I think is not going to be exactly what you expect. And we'll talk a little bit more about why. So I'm going to verify this first, make sure. So always got to verify and read the red love letters. So in the loop.
I think you have a missing semicolon.
Very likely.
Line 34.
Likely. So that one, yeah, correct. So always include those when you're typing. Very easy to miss. Okay, Sketch compiles now. All right. So I'm going to go ahead and load this. And then I'm going to see once it finishes uploading. Okay. So now I see blinking of the LED, which is a good start. So I'm going to open up the serial monitor and put my thumb over the A9 sensor, 566, 570. So obviously these are not scaled in degrees Fahrenheit. Now I'm going to cool off the surface using convection. So we drop to 550 back to room temperature. If we did something else, like I've got alcohol, I don't recommend you guys do this only because if you have like 70% alcohol, you can wreck the board. But the evaporating alcohol drops us down to about 500. Or even below, until it dries off sufficiently, and then we're back to values of, nope, still got a little ways. So 498. Okay, so we're still evaporating a little bit off the surface. These boards don't natively have a lot in the way of heat. So that's now mostly dried off. So yeah, we're sitting in the range of about 500 or so. Now, if I go back and touch it again, immediately we jump back up 540, 530, 540, 550, 560 almost. Yep, 560 and climbing. So the temperature sensor is getting a difference in signal. And then I let go and it drops slowly back down. So we'll probably settle, the resting state probably is somewhere around 520 to 530 or thereabout. So we know that we have control over the sensor, and by setting this up at 350 millisecond delay, we're able to still see what the sensor is doing. Now, obviously, even in Phoenix, it's not actually 527 Fahrenheit or Celsius, which would obviously be much worse. So the question is, what do we need to do there? And then that way we can figure out what's going on. All right, so yeah, like I said, about 525 or so resting state value. Okay, so the next part is questions on this step so far. We can see our data stream, we can see our data coming in. We're only about 42 lines of total code, including kind of some extra fluff in there, but we do have some comments in there to help remind us what it is that we're trying to do in the code. So questions on this part so far. Let's get a grand scale of clarity check. So again, one being dry dirt and 10 being holy water. Where are we at? How much sense is this making? It's not super scary, not probably as scary as you might have imagined. Okay. 6s, 7s, those are pretty good. All right. So now we're going to do some calibration. So this is where I'm going to treat it as if you guys haven't ever had to do a sensor calibration beforehand. So there's a couple things that need to happen. There are some programs or there's in one of the Playground Express libraries, there is a function that helps with this. But it's not really going to help in the way that you think it is. So we're going to do a quick step in actually, let me ask first. Do you guys remember? Let's start there. Do you guys remember how to correctly calibrate a sensor? This is something that you should have learned in the math lab if you had a good instructor. you should have learned the fundamentals of sensor calibration. This is one of the things that I wrote into the earliest versions of that course for a very specific reason. As an engineer, you are going to need to be able to think your way through how to calibrate sensors all the time. Does anybody remember anything about sensor calibration? Okay, learning these side by side. Yeah, I seem to recall not having that as a prerequisite, but we were going to, but we weren't. I don't remember where it ended up. Okay. So I will walk you through an example of what you need. We have some pieces of information, right? What are the pieces of information we have available? We have some data coming in from the sensor, right? So we know we have a range of values. You saw I was able to cool it off to maybe about 400 was the lowest. I was able to warm it up to about 570, right? So we have some values in there, but based on what we're doing with the sensor, how do we know what temperature is correct, right? So what we need to do is actually be able to access something like Excel. There are ways to do this in MATLAB later. I'm not going to do those right now. I'm gonna simplify things here in Excel. There's a couple pieces of information that we're going to need. So I'm going to come over here and build myself a tool, because this is something that you're probably going to have to learn how to use at some point in time, is how to build a tool like this. So in Excel, we know that we had a sensor value. We had an extreme range, and I'm gonna do some more alcohol bath and see just how cool I can get it. Why does that benefit us? So I'm gonna also have a note section. Estimated temperature is what we think this range is. So at body temperature, I'm going to hold on to this with my left thumb and try and let it equilibrate for a little while as we're starting to discuss this. So body temperature at thumb. What do we know about that? What should the body temperature at the thumb be approximately?
98.
Should be about 98 Fahrenheit, right? So we're going to say somewhere around, it's probably going to be just a little bit lower. It's maybe not going to be all that sensitive. Ideally, it's 98.6, right? So we're probably somewhere in the ballpark. We're not going to try and be all that super precise with it. We're going to clarify here that this is in Fahrenheit, because you guys have been accustomed to what the kiddies are calling freedom units. So we're gonna make use of those. So body temp at thumb, somewhere around 98. The sensor value here is, I'm gonna jump back over to watch. Another thing that can actually be helpful is I can close the serial monitor, and I can open up. You can only have one open, or at least in the previous versions, you can only have one open at a time. Oh, interesting. They're not showing on the serial plotter. Interesting. So the serial plotter is not outputting the same. Okay, interesting. So it looks like the high value is stationary around 583 seems to be the peak. So the average is somewhere around 582 for the sensor value. I'm also holding the back side of the board so there's no artificial cooling. I'm shielding it from a stream of any kind of stream of hot or cold air. So this is as reasonable as possible. Okay, so 582 might be somewhere around 98 Fahrenheit. The next one that we have is a second point calibration. And for most sensors, a 2-point calibration at least gives you a range of functionality that can work. So this one is room temperature. So we'll do a 3-point. So I'm going to set this aside on the desk, let it cool back off. I'll accelerate that a little bit. So room temperature, we'll use that in parentheses because this is again, this is an approximation. What do we think room temperature should be? Most of the time we're going to be in the ballpark of something like 74 Fahrenheit. Okay. So we'll take a look at what that reading looks like. When it stabilizes, I'll pull that value. I want to say that was around 555 or thereabout. I want to watch the data stream for just a little bit and see if it's trending in one direction or another. Yeah, 554, 553, 555. So it may come down just a little bit farther. And let's see. All right, so 550, it's stabilizing a little bit. 549. I expect it to stabilize somewhere around 550 because I seem to recall that was in the range. I'm not seeing a lot of values below like 549. So that seems to be maybe a stable region, but it's still dropping slightly. So what you would see on the graph is it still has a slightly negative slope, but the data stream that we're watching, the data stream that we're watching, it's stabilizing somewhere around 548, 547. So now I've got a couple in the 545 range. So it might actually be like 530 that was the stable point. So we're just trying to keep an eye on that and get an approximate range so that we can do some work with our equations. Because unfortunately, the breath coming out of your lungs is also approximately at body temperature. So trying to accelerate it that way is not particularly helpful. All right. So I'm seeing a really long trend here around 542 to 544. And I keep
had a
seeing.
question.
Yeah, go ahead.
My sensor is a little bit lower than yours. It's like stopping at around 525 to 530. Should we all, is it likely that we all have a different stable value
Yes, that is actually exactly what we should expect to see, because not only would we expect there to be plus or minus 1 to 2 degrees Fahrenheit variance on each of the rooms that we're in, all in different places, but also, so like I have an AC unit that is attempting to target a value somewhere around 73 Fahrenheit. That means that right here under the airstream, it's actually probably closer to about 70. And farther away on the other side of the room, it's actually probably closer to about 74, 75 at the walls. And so somewhere in the middle, there might be a temperature of 73 involved, maybe. But here I'm going to say, I'm going to make a call that we're stable right at 540. It might be a little bit lower in actuality, but 540, like it's really not dropping below 540 very quickly. So 540 is pretty close to what this is. And you'll see as we go to graph this, why this will make some sense. I'm now going to do the alcohol saturation and do that one more time to give me a third point for this calibration. If you've only got 2 points on yours, that's okay. 3-point should theoretically be a little bit more accurate and a little bit broader range. So I'm going to set it to where it can drain off the board without running onto the cable itself. But okay, so dripping with alcohol, let it just evaporate off. So I'm going to see how low it goes stably without any additional convection, because what I don't want to do is artificially bias the results there. So there you see we've actually gotten down into the 470s. So it seems pretty stable around, yeah, like maybe right at 470 is where it seems to want to sit. Oh, might go lower. So it's now dropping down in the 460s. I'm going to see if I can encourage it just a little bit. Okay, so somewhere around 460 or thereabout is a stable or very close to stable value with liquid alcohol. So liquid isopropyl. I also made sure to hit enough other spots on the board that it would work really nicely. So let me see. Um, okay. We are, yeah, enough of the board has been coated that it should be pretty well saturated. Okay, so it did get down into the 450s. All right, so I'm going to call it there at about 450 and see what we have and what that can do. 450, yeah. So 450 is going to be, I'm going to switch so that you guys can see. All kinds of madness going on when somebody calls you 6 times and cannot take no for an answer. It's never, ever, ever fun. All right. So 450. The next question is, how do we find out what the missing piece is for this, and what we need? So that was 450. This is at this is 91% isopropyl alcohol evaporating. And let's see. Yeah, so 450 is truly our minimum for just evaporation with no convection. So how do we find that? How do we find this one last piece of missing information for what that temperature ought to be? Any ideas?
You could Google it.
Yeah. So somebody that's really sharp at Googling things, tell us what the temperature of evaporating isopropyl alcohol is. Like, is it freezing if you have alcohol evaporating? Does it turn whatever's water is next to it into ice? What happens? Yeah, depending on airflow, that's valid. So isopropyl alcohol, let's see. This is a little bit of a trickier question. The 91% in that is important. And there's a couple ways to calculate it. But yeah, you're probably looking at, somewhere on the order of 60 to 65 degrees. In my example here, because it will evaporate. Let's see. Because its boiling point is often below what room temperature is. Yeah, those references are not particularly helpful. I'm also at a different vapor pressure than you guys are because of altitude, which adds a level of complication. But again, this is an example of what you might have to do for a real engineering sensor in the field. Let's see. Yeah, that there we go. Unfortunately, that doesn't include a temperature measurement, so that doesn't help either. Yeah, there's a couple examples. I was hoping to not have to go all the way back to a TXY diagram. But I'm also not doing a vapor pressure measurement. So yeah, we're probably in the, because of the latent heat that it is absorbing, we're probably going to be in the ballpark of about 60 Fahrenheit. You can elevate the temperature basically up into the boiling point at a given vapor pressure. It changes a little bit as a function of the vapor pressure, but it's normal. Yeah, the normal boiling point. And instead of having to go to a physical chemistry reference or calculate things based on a TXY, one of the key aspects of this is the amount of heat that it is absorbing. So it can absorb a certain temperature. So I'm going to use 60 as a starting point, and then let's say 65 degrees as an estimation for that. I can be a little bit more specific. So the part of the issue is because I'm at a lower pressure at this particular altitude. This should be probably a little closer to about 65 degrees steadily. So what we'll do is we'll graph this. So we're going to insert a scatter chart because I don't want to have to teach you guys sort of all of the rest of chemistry. And what we're going to do is we're going to right click somewhere in the chart and we're going to do select data. I'm going to remove everything that it pre-populates and add my own set. So this is going to be temp
I just
calibration.
wanted to say real quick that we can't see the pop-ups that are on your Excel.
Yes, it will show up in a second because of the frustration. I can switch it to a windowed mode that'll help so that you can see. And then jump out of the infinity mirror here. So the X values, I can't show these any bigger because reasons. So you want to pick X and Y values carefully when you're doing calibration. Why? Because we're going to do a fit line, and you're going to want to express the fit line on the graph itself. That means that you want to format it in such a way that the value that it gives you, you can plug in whatever the X data range is. You can plug in a value for X. In this case, we want the sensor value in X so that we can plug in that same formula in our code to be able to output in what we think is approximately degrees Fahrenheit. Okay. That means that for X, we need to use the sensor values because that's the thing that we want to plug into the formula to output something in Y, which we need to be temperature. So you want to delete the thing that's there originally, and we want to plot these three things together. Okay. We want to rescale this range. We want it to be automatic. We want the major unit to be 100. We can do the minor unit as something like 50. The minimum for us, just to clean things up a bit, needs to be about 400, with the maximum being about 700. And this way we get a reasonable range. So 65 for this low range of about 450 is an okay estimate. It's, again, I think at this altitude it might be a little bit closer to 60 degrees or thereabouts. But anyway, we will get a reasonable enough fit line here. What we're going to do is go to add trend line. It's going to be linear. We're going to do automatic. I'm not going to force the intercept to 0 or any of those tricks that I would normally do. But I do want to display the equation and the R² value on the chart itself. So what that does is allows me to see what this value is, and I can take that and I can use that formula in our data. So even if that were 60, it's not going to be hugely more in line. But anyway, this will give you an idea. Also, this thermistor curve may not be entirely linear, but what we don't want to do is just fit a fit line that makes our data work if a couple values higher makes this go somewhere strange, and yeah, it's not good practice. So we're going to copy this. So I'm going to copy this, and that's what we're going to paste into our code. So I'm going to switch back over to our code, drop this down. So we're going to come back to this. I'm going to go ahead and close the serial monitor for now. I'm going to add this in and say we're going to take the sensor value, we're going to do the analog read, we're going to do the write to pin high. Then we're going to do a redefinition of the sensor value based on this formula. Now equals, so this is going to be the other half of that formula. And we're going to close and go to the next line. So the sensor value is now going to be this value times sensor value minus 36.7. So this operation is going to change the value of our is going to change the value that we're storing to sensor value. So what we're doing is then we're going to print the sensor value, and we're going to maybe even do a print, follow this up. Degree F. And we're including a space. So we're including a space in the string here. We're doing the sensor value, including a space, and then the string here. This will allow us to see the sensor value. So this use our calibration curve to estimate conversion to degree Fahrenheit. And then this displays temperature in human readable form. And that's what this is doing. So now we're going to check to make sure this will compile correctly. Of course it will. And we reload this. Then as soon as we're back up, we're loading, we're done uploading. Okay. So now we go to the serial monitor, and it says temperature is 81 degrees Fahrenheit. So we can see that we're maybe not exactly, but if I hold it, let's see what it goes up to. (91 degrees Fahrenheit). So we're not an exact fit. 92, it's probably going to go up a couple more, 93, 94. So that part of the range is probably not super far off. But if we let go and let it return to room temperature, or we add some of our alcohol to evaporate off, so it should be probably a little closer to about 70 degrees. But the reason it's not is because a lot of those readings are going to be in this range. And what we actually saw was down here So this value for the alcohol is very likely incorrect, based on how cool it can actually get. So this value, that's one of the only ones that we're doing an estimation on. And really, this might actually be a 75-degree room right now, but this might actually be at this altitude something like 55 degrees. So this would be about a 0.94 fit, which is a little closer. It might even get down as low as about 50 degrees because of the latent heat that it's pulling out. But it's going to line up best with this linear arc if it were actually about 40 degrees. So if I use this value, just as a for instance, and I replace our code with these values. So I say, I'm going to cut that part of it, paste it here, and I'm going to cut this part of it and paste it here. Then I'm going to get rid of that gibberish. All right, so now if I re-upload it and then I watch for the serial monitor, so I bring serial monitor back up. Now it says it's about 61 degrees because it still has some alcohol on the surface. If I remove that and bring it back up to body temperature, we should see 90 some degrees for body temperature. Okay, so it's responding. So if I let it go and just sort of return to room temperature, let's see what it does there. So now it's dropping down below 80 degrees, somewhere into the 70s, about like what we would expect for it to do. Okay, and we see that it's printing out with our value and then degrees Fahrenheit. So this is giving us perhaps a little bit more accurate range for temperature. So the thing that's going to be different for each and every sensor is these values. So the format is, again, the y equals mx plus b. So that value is going to change a little bit for each and every individual sensor, and proper calibration is what's going to give us meaningful data. So this says about 74, 73 degrees, which is right about what it should be, really literally sitting under this particular air conditioning unit. It should be about 73 to 74 degrees Fahrenheit. So we have a reasonable accuracy now, at least around a single temperature point, but also around a couple of other points that help us to get a better idea of what's going on there. So for you guys, what temperatures do you guys have for your room readings currently? Let's see what values you guys are getting. So if you've got a reasonable calibration and you're somewhere in the probably low 70s, you're probably pretty accurate, especially if you've just got the 2 points of calibration. Just for the sake of demonstration here, what I'm going to do is I'm going to eliminate, for the data set, I'm going to go back to select data. And I'm going to edit this, and I'm going to take one away. So I'm going to do to A4 and B4 instead. So that calibration would be about 0.54 and minus 220. So with a straight line, you should get a pretty reasonable calibration. You should get an R squared of 1. If you don't get an R squared of 1 with 2 data points, you really have a real problem. That was a science joke that maybe some of you will get on the way home. That's fine. So we've got some 70s, we've got some low 70s. The point here being, with a 3-point calibration, I have a little different value depending on how the calibration is done. That will determine the precision and the range of use. So if you were to go stick your Arduino somehow still connected to a battery pack or something like that in the freezer, probably your low range would be out of calibration because you've only got a 2-point calibration at the high end. So this gives you some sort of a reference point to be able to work with. And if I switch back over, our values of 0.43 and minus 155 are probably pretty close to accurate. So the true value might be somewhere in the middle, maybe a little less than 0.5 here, and a little more than minus 155, might be 175, 180, something like that. So that gives you at least a reference point for how to take a sensor value and then correlate it with what it should actually be. Because now it says, now that it's sitting in the room, all the alcohol is evaporated. It has no other, it doesn't really have much direct airflow. Sitting somewhere around 75 actually feels probably about right for where this room is at the moment. I, of course, don't have a more accurate thermostat available, so I have to go based on what it feels like. And so I think 75 is pretty close to accurate. So I would say this is correct at this temperature range. It's pretty close to correct for the thumb contact because your skin won't be 100% at your core body temp, might be a couple degrees cooler, especially at your extremities while you're working. So this is at least calibrated within a reasonable range. This is a believable, passable number. There are some functions that can do this in a single step for the Circuit Playground Express. We're not going to learn those functions yet because we want you guys to understand what that calibration process looks like when you have to go to work on a sensor that doesn't have some sort of existing library that you can reference. You can develop this stuff yourself. You just have to be able to think a little bit outside the box. So I had to build myself a little quick Excel tool to be able to develop this custom formula. But once I did, I was able to get it calibrated within a couple minutes of what probably close to actual temperature is. So, all right, on this example so far, where are we on the clarity scale? You guys getting this? Is this making sense? Have we transcended OG Gatorade flavors and we're now into the Crystal Light flavors, somewhere around the 7s? Or where are we at? As long as we all acknowledge that Crystal Light isn't actually even a real drink. We're going to do a lot more stuff with input and sensors, but this should at least give you guys a pretty solid reference point. Clarity of raw egg white. Okay, that's fair. So that's probably, yeah, raw egg white is, that's probably like an 8 or a 9. Yeah. Yes, those are, the Crystal Light is usually like a powdered, it's sort of supposed to be like a lemonade, but without sugar, and it's marketed as like a fit housewife drink or something. It's like marketed as lemonade, but without all the sugar and also without all the lemon and anything else that actually makes lemonade. So that's an issue. On campus, the The IT folks will be completely unable to help you for board related problems. That's really going to be limited to instructors who can help you with those. So you'll try and find somebody that's got office hours. I don't know offhand who else is teaching programming this semester. Some of the folks that have taught programming aren't continuing to teach that this semester. So I don't know who's currently on the slate for that. Because you will need to be able to pull sensor data in. If some of you continue to have problem after problem after problem with your boards and you still have your Arduino Unos, I would recommend at least there's some problems that you guys are going to work on. So like this one today, there is a thermistor in the Arduino Uno kits that you guys get, for instance. There are some guidelines online for how to build a temperature circuit. There's also one of the labs that we use in the math lab that will allow you to build basically the same kind of circuit. You have to have the thermistor and another reference resistor on the circuit. So it's a couple additional steps because you kind of have to create the circuit that's already on the Circuit Playground Express, but then you can still run the same physical code. You would just change up here which pin the sensor pin is based on what you're running it into. You might still use analog 9 just to keep things simple, but you might output a different value for the pin or something like that. So you can recreate the circuit and do all the same things with those Arduino kits for the most part. So if you're really having trouble with one board and no instructor can help you, making the circuit that you need for that particular problem set is going to be your next best bet. There's tons and tons and tons of examples using Arduino Unos to build simple sensors like temperature sensors online. So those are ones that you want to go looking for. All right. Other questions on this? Sounds like most of you guys are getting this and it's making sense. There are some examples here where you're trying to make all of this work and function. The next question is going to be, we're going to start taking some of these concepts and we're going to elevate kind of the level of difficulty a little bit for the next, one of the next steps, because we've got a simple example here of a single sensor input, but we want to start elevating the sophistication of our output. And that is going to require some more Circuit Playground commands, because we want to be able to do things like turn on the NeoPixels and set their values and some of those things. So that's going to be some of the next progression, is how to do output on the board based on the input, but still have the serial monitor running so that we can see what the data looks like, because the red LED blink, 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 blink doesn't really tell us a lot about what the temperature is, right? Is the temperature higher? Well, probably this would need to blink faster. Or maybe we could just use the LEDs. The more LEDs are filled, the more, the higher the temperature, the lower the temperature measured, the fewer the LEDs are turned on, something like that, right? So we're going to look at some of those sorts of things next, because that's going to get us the pieces that we need in order to do some more sophisticated programs down the line. So I wanted to make sure there were no other questions before we start looking at what's involved there. All right, so the next step I don't see any questions coming in. So the next step is going to be there are, I know there are a list of commands. I'm still trying to locate some of those because I just haven't had an opportunity to go looking for them again. There we go. Okay. I'm going to look and see real quick. I know I dropped a couple files in here. We're going to do some other pretty interesting projects later in the semester. And we will be working on a quiz just to make sure that we've got an idea what you guys are doing, and make sure that you guys have an idea what you guys are doing. Let's see. There are a couple functions, but that's not where it is. Let's see. There's some instances pretty soon where we'll give you some broken code and have you do some troubleshooting on it. Where is that? If only I had an office assistant who could answer people angrily on the phone. That'd be great. Yeah. Nope, I don't see any examples there at all. Okay. So I'm going to do a real quick look. Because I can teach you how to pull what you need out of the library. But there's going to be a few, and I know I posted the PDF, but I don't think that one has all of the moving pieces that are needed for you guys. There we go. Let me see what I can find here. There's not additional attachments. So I'll have to look and see because I don't see it there. I'm going to see if I can pull it up here real quick. The functions, there are a bunch, and there's some specifically set up in the library. However, Um, yeah, that might be the closest I can still find to a command list, but does it have the command list? It has a couple, let's see. In mode, let's find out. F. Yeah, it's not actually attached. That's a problem. So I'm going to include this to an announcement for you guys so that you've all got it as a point of reference, because you're going to need it. That will help to make things a little bit easier to get a hold of. Let's see. So this includes some example command structures. To example command structures. Go. So that's attaching at the ever rapid speed of Halo, but it should at least give a couple pieces of useful content. I'm going to let that decide what it's doing for a second or two. I'm going to look and see. There we go. So there's a few. Trouble is a lot of this will have some reference in Python. But there's some more that are helpful. Let's see. No. There's a couple more, but I wanted to see if they included the Java, because I'm trying to not have you guys have to read the library files, but there may not be much of an example. Yeah, because that's in Python, and that won't be as useful. That does some pin naming. And the commands are very similar. Okay. So I'm going to have to pull it from one of my old examples because it's not actually included in this reference. I will go ahead and post this for you guys because I thought this was already attached. There we go. It'll finally allow publish now. That'll at least give you a starting point, and we'll see what we've got. Yeah, I'm gonna have to pull it from a language reference. All right, well, unless I've got another file, which I might, just because I'd rather not have you guys spend too much extra time chasing some of this down. Let's see. Yeah. So there is a couple. We're going to do another example later. We're going to use the microphone input as well. That'll be a little bit different. So that's going to require a different kind of approach. We're going to do some calibration with the light sensor and a couple others. I'm looking for a specific one. There we go. That will be the easiest way to do it. So there's not the one I was hoping for, but similar. Okay. So I'm going to get you guys started on this. And we'll include a couple differences. I don't want to confuse you by adding a bunch of other unnecessary steps to the process. So let me go here and do it this way. So we're going to go back to analog input as a reference point. We're not going to resave with the same name for this file, but I'm going to copy over some additional material here that will help make sense of things. So I'm going to include a couple of libraries at the beginning of this, and hopefully I've got both installed. That will be immediately obvious when I verify whether or not it can find both of them. Yeah, it looks like it did. Okay. That should be included in the zip folder that I gave you guys already. So making sure to include those in your libraries, which you download them, then you manage libraries, and you find where they are. You can also add libraries by copying and pasting them into the libraries folder. You can include library, manage libraries. You can also add zip libraries, which is the format that I gave you. So there's a lot of options for how to do those. Specifically, the Circuit Playground is the one that I'm using as a reference. For now, it's going to be easiest to start with a couple of functions. So I'm going to close out the library manager here. It's going to be easiest to start with a function. We are going to have to include circuit playground .begin in our setup. This starts certain this starts certain library functions for specific to the Circuit Playground Express in order to make them available in the code. All right, so given that, what we've got is we've got a variable, then we need to set let's see, we need to make use of a loop structure to work with the pixels, but I want you guys to see what that function looks like. So we're going to use another variable, n as an integer. So this is going to require adding a concept. There's really no easy way to do that. Each iteration of the actual loop, there's really no sort of shortcut to this. Each iteration of the loop, instead of simply digital write for the LED on high, I'm going to resave this as a new value. And this is going to be Circuit Playground Express CPX. CPX temp neopix is what I'm going to save this as because reasons. You don't want to try and save over the default file just as a general rule. And I think in a lot of cases it won't actually let you. But you want to try and not save over example code. You want to save it to your local working folder. So we begin the Circuit Playground to make some of the code available. Instead of this for the digital pin high, we're going to eliminate that. So this sensor pin to input, that's fine. LED pin to output. This we're going to get rid of because we're no longer using that. So for the moment, I'm going to comment this out, and that will start some of this. We're not going to use the LED pin. We're not going to do this digital write. We're not going to do this digital write. So we're going to comment those out just by adding the double slash in front of them. We're going to be doing reading and converting to temperature. We're going to be printing the value. Then before we do the delay, we're going to be adding in a new structure here that I think is going to be, it's going to make sense why we're doing this once we get there. If else, so if else for, so what we're doing here is a for loop. This is a really important type of content. We're going to go from, there's a couple pieces to understand here. I'm just going to set my range first. 0 less than or equal to, there are 10 neopixels in total. So I'm going to go from 0 to 9 because it's actually indexed 0 through 9 because reasons. The circuit playground set pixel color. You set in the set pixel color. This requires a couple things, and pulling this up rather than walking through the library and trying to understand and interpret from the library is easier because reasons. So this is a function that sets the color of the neopixel. Pixel 0 is the starting pixel next to the GND pin. Pixel 9 is above the pad labeled 3.3 volts. There's a parameter of 0 to 255 because of counting in binary. 255 is a maximum value. There's 0 is off, 255 is max. So this is just like the PWM output on something like a computer fan. The max output is actually 255, not 100, because of the way that these values are calculated. So the parameters, so if you set the first one, so it's the R red, G green, and B blue component values on a scale from 0 to 255 is what you're doing here. This also sort of sets the intensity because the brightness of the neopixels just is what it is. So if there's a couple layers to the structure here that will make some more sense as we get into some more details about loops and things later. For now, these are going to help get you an idea what these do and how they function. So for an integer value, n is just the number for the neopixel. For n equals 0, for n less than or equal to 9, keep incrementing all the way up to 9. You can basically copy and paste this structure for a couple different levels. So if our sensor value is what we're going to be using as a reference, if our sensor value gets to be above a certain threshold, we want all 10 to light up. So this for loop can go in its own structure where if the value is above this certain range, then do this thing. And what we're going to say is for integer 1 through 9, if this is a comparison, this is for doing some even number division. This has to do with a remainder. So we're not going to use this set of conditions, but we can change the color based on what is happening here. So if the value, sensor value here, sensor value is, we're not going to do comparable to, which is the double equals. If sensor value is 75, then the neopixels, I'm not going to do the more complicated version of running a number of neopixels based on the scale of temperature yet. That's when we're studying some more about loops and structures. That's when we're going to get to that. I'm going to simply do color today so that you guys can at least see them and see how to use them on the board. So if the value is greater than or equal to 75, then it's going to be set the neopixels to, we're going to do about 180 on red, 0 on the other colors, because reasons. Else, if it's below 75, so if it's, yeah, let's do above 80 and say above 80 is hot. Unless, of course, you're from California, in which case you probably think that 75 is like the end of the world. Why that's the case, I'm not real sure. We're going to do an else if sensor value is greater than or equal to 70. Let's see. It's greater than 70. Then it's going to be green. So this now sets all pixels red if over 80 Fahrenheit measured. This sets all pixels green if between 70 to 80, 70 to 79 is measured. '70 to '79 is measured. Else, and this one does not require its own crazy value. So we're going to set this also to be 180, and we're going to do this one to, we're going to say 0. This is going to be 180. For blue, so this pixels blue if below 70. Okay, so this is a simple example of how to use a value, and for each one, as it varies, because of how this will work, this will go through very quickly, and inside of the loop, the way that this is timed, this will fill up all of the neopixels very quickly, assuming it compiles and works correctly. So I'm going to check, verify that it compiles. It should, because I don't have any I shouldn't have any glaring errors on this. Let me see what line. If sensor value else. Memory limit. That's interesting. That shouldn't hit a memory limit. Why is that hitting a memory limit? That's super bizarre.
Does it have to do with the for loop?
No, because this has enough storage space. I'm going to see if I can go ahead and load it anyway, because it shouldn't actually be out of memory at all. It's 12 and 14% of the dynamic memory space available on this unit, and it should be just fine. So right now, this is again an instance where this is doing stupid Arduino tricks right now. You can see this is all red. We'll look at what the serial monitor shows. So 78, 80, 80, 78, 80. We can cool this off and see. Yeah, it's not going to cool off without. So upon contact with alcohol, we're now green. And if we cool it off further, there we go. We switch to blue. So the memory limit there is not actually a real issue. This is another one of the reasons why I was not really a fan of trying to use this particular board, because it would do weird things like this. Upon warming it back up, goes to green, back and forth to blue, depending on how much alcohol is still there. So green, back to blue, then we touch it. Green, back to red. Let go, back to green. 70 some degrees, somewhere in the middle, because it's still fundamentally cooled off. But even if I hold on to the back side of the board where the sensor is on the front side of the board, it'll go back up to green, and it'll go back up to red above 80. It's going to reach there shortly. So it's about 79, 80. There we go. It's red. If I let go, it'll drop below 80 and cool off down to 79. So it's switching based on the values that I leave there. So it probably doesn't have enough alcohol to drop down below 75 again. But that lets you see what the actual pixels look like. And the reason I'm not using 255, I'll show you as an example. Running anything at its absolute max brightness is a good way to shorten the lifespan. So I'll go ahead and load this. It'll compile anyway because reasons. So green is a certain level of brightness. So now it's registering. But if I change, so the intensity of red is greater there. So the brightness level is higher. So it's easier to visualize, but it's not necessary. You get almost the same effect at 180 as you do at a lower level. You can also go down to around 100 and it still lights up sufficiently. So the higher value that number is, the harder you're pushing the NeoPixels and the shorter their lifespan will be in the long term. So it's just not necessary to run everything at 255 all the time, because not everything is a Hellcat and it doesn't always have to erase tires. That's why. All right. So questions on this? Are you guys starting to feel a little bit more comfortable? The libraries that are installed are the ones that are at the top of this list. So it's Circuit Playground Express library. They're in the zip folder.
Yeah, I was looking. I found them already. Thanks, though.
Yeah. Okay. Yeah. Circuit Playground and Circuit _ Playground is the two that we're working from. All right. So I know you guys are now completely turned into vegetables. Any final questions as we go to close out for today? Yes, we will need to get a quiz on the books this week, just so that we're tracking with the general flow of the semester. There's a lot of individual assignments on these, so there's a lot to do. So I will get you guys information as soon as possible on what that will look like. But the quiz is only going to cover concepts that we have clearly covered and had you guys do in assignments. So if you've been doing stuff and following along and not just sleeping next to your phone with everything on mute, you should be fine. If you're sleeping on your phone with everything on mute and not actually following along, you should be gravely concerned for the quiz. It's really that simple. All right. Beyond that, any questions?